All right, I think it's recording now. All right, so yeah, so this is section 7.5. So yeah, so we discussed yesterday, we discussed the central limit theorem. So we said there are two versions of this theorem. The first version is for normal distribution. So I'm gonna just remind you very quickly the two versions of the theorem. So version 1. So this is for a normal distribution. Normal distribution. All right. So you have your variable x. So x represents a random variable. So x represents a random variable. Random variable which follows a normal distribution. So this is x follows here a normal distribution with population mean mu. So we have population mean mu and standard deviation sigma. Standard deviation sigma, and then we said sigma. And then we said if you take a sample of size n, now we take a sample of size n, right? And let's say x bar is the sample mean or the sample average. X bar, this is the sample mean or sample average. Then so then the theorem says the following. So the conclusion is the following. So then x bar actually follows a normal distribution, can be approximated with a normal distribution, follows a normal distribution, and with population mean the same as x. So it's the same mu, but the standard deviation is different. So the standard deviation would be sigma over square root of n. Deviation sigma over so sigma over square root of n. All right, so this is a first version. In the second version, so the difference, so in the second version of the central limit theorem, your x follows a random probability distribution. So this is version 2. So this is for a random, so this is for any probability distribution. It doesn't have to be a normal distribution, right? So it's just a random probability distribution. So this is for any probability distribution. Right, so you have your variable x. So x represents a random variable. Same thing, but it doesn't follow a normal distribution, right? Here x just follows or some random probability distribution. So x represents a random variable which follows, a random probability distribution with population mean mu and standard deviation sigma. Sigma. So again, the difference between the first and the second version, in the first version, x follows a normal distribution, right? here in version 2, the probability distribution is not necessarily a normal distribution. It can be any probability distribution, right? Now, the second difference is the following. So when you take a sample here, you need your sample to be of size larger than 30. So take a sample. So here we agree that the sample has to be of size n, larger, more than 30. More than 30. Okay. Otherwise, you can really approximate your X bar using normal distribution. Then of course, again, X bar is your sample mean. And we're going to have the same conclusion as version 1. So then X bar will follow a normal distribution. So then X bar will follow a normal distribution. So in both cases, the X bar is going to follow a normal distribution, even if your X is not the normal distribution. Okay, that's why this normal distribution is very important. So as you can see, in both cases, the X bar follows a normal distribution. So then it follows a normal distribution. So then we can convert this X bar to Z, right? That's what it means for us, right? If it follows a normal distribution, then we can convert the variable to Z. A normal distribution with, again, population mean, the same population mean, so mu as X, and standard deviation sigma over square root of n. All right, guys. So I think we had at least one example yesterday. So we're gonna do more examples. At least one more example. At least for for this second version, I think we didn't have any example where the X doesn't follow a normal distribution. So yeah. So let's have an exercise for an example. All right. So let's say we have example. So this is actually exercise from the textbook. Example or exercise from the textbook. So this is actually exercise 18, page 346. So it says the following. So X here, X represents the dollar amount spent on supermarket impulse buying, and in a 10-minute, let's say in a 10-minute shopping interval, 10-minute shopping interval, right? So the mean of the X distribution is, so you see here, X doesn't say that X follows a normal distribution, right? So here X, so let me just remark here. So X here doesn't, right, follow a normal distribution. I'm not saying X follows a normal distribution. Right? So it says that like the distribution or the X distribution, the mean, the population mean of the X distribution, mu, is actually equal to, it says how much, is about 20. $20. Okay. And so that's the average. And then the standard deviation. The standard deviation is sigma. Sigma is actually $7, right? So now it says we need to consider a random sample of 100 customers. So consider a random sample of 100 customers. Okay. Each of whom has 10 minutes of shopping interval, etc. So what can you? So the question is, so what's the probability that? So what's the probability that X bar so that's the sample mean or the average amount spent by the 100 customers. So what's the probability that X bar? So X bar, this is X bar. So this is the sample mean. Sample mean. So this is the average amount spent by the 100 customers. Right. So we have this random sample of 100 customers, right? So what's the probability that this X bar, which is the sample mean, is between, let's see, $18.22 is between.
Professor, I have a question.
Yeah, please.
How do we know that of any exercise that X doesn't follow normal distribution?
Okay, that's a good point.
Or the exercise is gonna tell us that X doesn't follow.
No, so when you read the exercise and you don't see like X. So if it doesn't say X follows a normal distribution, then X doesn't follow normal distribution. Like here in this exercise, you see in this first part, the first part of the exercise right here, it doesn't say X follows a normal distribution, but X is normally distributed, right? So there's nothing here which says that there is a normal distribution, right? In this first part, right?
Yeah.
You don't see any normal distribution here. It doesn't say there is a.
If it wasn't a distribution, how would it stay on X?
Oh, yeah, it would say, for example, X represents the dollar amount spent on supermarket, etc., and X actually is normally distributed, for example.
Oh, okay, got it.
Okay, it would say like X is normally distributed or X follows a normal distribution. So it's going to tell you that X is going to follow a normal distribution.
All right, okay? Thank you.
So yeah, sure. So yeah, so this X bar, you want to find the probability that this X bar is between $18 and 22. So as we said, guys, here in this case, your X doesn't follow a normal distribution, so we need to use this version number 2, right? This version number 2, it says your X represents a random variable with population mean, etc. So it doesn't say like X is normally distributed. So to use this version 2, you need your sample to be of size and larger than more than 30, right? 30. And as you can see in this exercise 18, it says, so we have this random sample of 100 customers. So of course, 100, that's larger than 30, right? So, yeah, so as a remark here, before answering the question, so as a remark, So the sample here, the size of the sample is 100. So the size of our sample, of the sample in this exercise is 100. We have 100 customers, is 100. And that's larger than 30. That's larger than 30. 30. Okay. So if it's larger than 30, then we can use this version 2 of our theorem. So we can use.
And if it's not larger than 30, we use.
No, yeah, if it's not larger than 30, actually, this X bar cannot really approximated by a normal distribution. So you're gonna get something which is not true. So if it's not larger than 30, you cannot really use a normal distribution here. Then you can use something else. We're gonna actually discuss it like in a chapter 9, I think.
Okay.
Okay. Yeah. But in order to use the normal distribution, you need something more larger than 30. So yeah, so then we can use here we can use version 2. All right, so yeah, so we to answer now the question, and this is the answer. So you wanna find the probability that X bar is between 18 and 22, right? So you wanna find the probability that X bar between 18 and 22. So because in the second version of our theorem, of course, this X bar follows normal distribution. So then it means you can convert this X bar to Z. So we can convert X bar to Z. So as usual, so here's the Z. Now to convert this 18, just to remind you, so the Z would be equal to X bar minus, so it's the same mu as X, so minus mu over, now the standard deviation is different, so it's sigma over square root of N, where N is the size of the sample. So yeah, so so that will be 18. So here it's going to be 18 minus mu. So in this problem, mu is 20, right? The mu is 20, and the sigma is 7. So minus 20 over, but then it's a sigma over square root of N. So 7 sigma over square root of N. That's 100. Yeah, 100 square root of 100. And same thing on the other side. So it's 22 minus the same number, this mu over 7 over square root of 100. Now, guys, take your time when you compute this thing here, these fractions. So first, subtract in the top. Yeah, so you have your, they have the probability that, so 18 minus 20 in the top, that's -2. And then we have this 7 over square root of 100. So square root of 100, I mean 10 times 10 is 100. So then square root of 100 is 100 is 10. So this is actually, so 7 over square root of 100, that's 7 over 10. And 7 over 10, of course, is just 0.7. So in the top, you have -2, and in the denominator, or in the bottom, you have 7 over 10, which is actually 0.7. So this is 0.7. Then Z, and then +2 over the same thing, 0.7. All right, so again, guys, this 7 over square root of 100, 7 over square root of 100, that's 7 over 10, that's 0.7. That's how I got this, the denominator, this 0.7. Anyway, so then we can just divide. So this would be, of course, so we have 2 over 0. minus 2 over 0.7. So that's actually negative 2.85 z. And then the other side is plus 2.85. So once you're done with the fraction, now you're supposed to use the chart. But again, here your z is between two numbers. So when it's between, so z between, then between two numbers. So then you're supposed to take the second number, always the second number. So we need to switch. Take the second number, z less than the second number, minus z less than the first. Because the area between two numbers, that's the area to the left of the second number minus the area to the left of the first. Now we can use our chart. Right, I think I'm going to just show you again. So for example, for 2.85, again, the chart is, the formula sheet is on CUNY Blackboard. So for 2.85, you go to 2.8, positive 2.8, and then nearest hundredth, it's 0.05, 0.05. So
9978.
Yes, 9978. Thank you. So it's 9978. Now for negative, you do the same thing. So I think it's where is it? So for negative 2.58. So that's negative 2.5. Sorry, negative 2.8.
0.0022.
Yes, 0.0022. Thank you. So minus 0.0022. So the answer is 0.9956. So in other words, that's 99.56%. Okay. Yeah, so so find the answer, of course. So probably that X bar here is between 18 and $22 is 99.56%. All right, guys. Now, if you suppose that X, so now let's say in B, if we suppose that X has a normal distribution. So if we suppose that X has a normal distribution. Okay, so like the first part of the question or the exercise, for example, let's say X represented the dollar amount spent on supermarket, etc., and X follows a normal distribution. So you know that X follows a normal distribution, right? So if your X follows a normal distribution, then you're supposed to use the first version of the theorem, right? So then we need to use version 1. Then we use version 1 of the theorem. Okay. So and so let's say I want to find this probability that, I'm sorry, I guess I need to mute someone. All right. Sorry. Yeah, so let's say you want to find the probability that X bar is between 18 and 22, right? So you want to find probability that X bar, same question, right? But as I said, here we suppose that X follows normal distribution, right? So in that case, we use the version 1. So in the first version, where is it? No square root of n here. And so in this first, where is it? Yeah, first version of the theorem, right? So here your your X follows a normal distribution, right? So then so X, so we can convert again X bar to Z, and we can do the same computations, right? So we can do convert X bar to Z, and we can do the same computations. Okay. So I mean, so there's no difference. There's no real difference between the two versions, except that, like in the version 2, there's this restriction on the size of the sample. Okay. So yeah, that's the unique. That's like basically that's the difference between version 1 and version 2. When X follows the normal distribution and when X doesn't follow the normal distribution. Okay. So the only difference is that in version 2, when X doesn't follow normal distribution, there is a restriction of the size of the sample, right? But the computations are just the same.
So the computations is not the mean minus mu over the standard deviation?
Yeah, yeah. It's over the standard deviation, yes. Yeah. But for the X bar, this
For
is
the X
for
bar, we
X
use
bar.
one with the square root.
So with the square root. So it's
So
again the
every
same
time we
thing.
see the X
The
bar
X bar, yes.
is square root.
Yeah.
Without
So
it, the other one.
yeah. So whenever you see X bar, it's always minus the mean over your standard deviation over square root of n. Or so like in this exercise, of course, it's square root of 100, right? So it's just the same computation, the same thing. You have your Z here, and again you have this. Sorry, was 20 the mean? So the mean was 20, right? Let me just see again. Where's the mean? The mean is, we said, yeah, it's 20. So yeah, so it's 18 minus 20, of course. This 20 here. Minus 20 over 7 over square root of 100. And the same thing on the other side. So it's 7 over square root of 100. Okay. So we're going to get the same answer. Yeah, so whenever you see X bar, it's so minus the mean over, and then we divide by sigma over square root of n. Okay. So yeah, and as I said, we're gonna get just the same answer, which is 99.56%. Okay. It's just so here I'm just saying, because if your X follows the normal distributions, then what we are using is version 1, not the second version, but the computations are just the same. Okay. All right, guys. Is there any question, guys, before moving to the? I guess we can do an exercise from the textbook. Let me see. All right, let's do, for example, for example, 13. We can do 13. We did 14, I think, yesterday. So let's do exercise 13. And then we can probably move to the next section, right? So 13, page, this is 344. All right. So here, what does it say at 13, page 344? So it says the following. So coal is carried from a mine in West Virginia to a power plant in New York in a hopper cars on a long train, etc. The actual weights of the coal. So it says the following. So the X represents the weight. You see the actual, so the weight of coal loaded into let's see, hopper car, and yeah, in a hopper car. So on a long train. And we suppose that X is normally distributed. Yes. So it says we suppose that X is actually normally distributed. So X is normally distributed. So you see here, we have this hypothesis that X is follows a normal distribution, normally distributed. All right, now the questions. So A, it says with the, of course, with with population mean mu. Mu equals to let's see, 75 tons, and standard deviation sigma is equal to, let's see, 0.8 ton. So it's 0.8. So 0.8 tons. All right. So A, it says, oops. So A, it says, what's the probability that one car chosen at random will have less than 74.5 tons of coal? So what's the probability that a car chosen at random car, of course, will have less than, yeah, okay, we'll have less than. So again, guys, there are like three different cases you can have. Like you can have like less than, right, more than, or between. Okay, just keep in mind there are three different situations, and of course the way to answer each situation is kind of different, right? But anyway, so let's say here we have less than what is it, 74.5 tons of coal. B, okay, in B let's do more than. So in B, so what's the probability that 20 cars, we choose a random, we take a sample of 20 cars. So what's the probability that 20 it's 20 cars,
This is on blue line.
20 cars chosen at random will
They don't
have
want people to panic. Trust the law enforcement, police,
more than,
effort to get this person off the streets.
yeah, I guess I have to move someone. All right. So we'll have more than, let's say here, more than. We'll have more than. We'll have actually mean load. A mean load, so average load, X bar, more than 74.5 tons. Oops. 74.5 tons of coal. All right, guys. All right, so I'm gonna give you a couple of minutes to think about this exercise. So here X is, as you can see, it says X is normally distributed, right? So there's no restriction on the size of the sample. So you see here, like in B, we have this random sample of 20 cars, right? Of course, 20 is less than 30, right? But in this example, so in this exercise, it doesn't matter that 20 is less than 30 because our X is normally distributed. So we don't really care about the size of the sample. All right, so I'll give you a couple of minutes to think about this. X normally distributed, mean is 75, sigma is 0.8. In A, the probability that a car, just one car, a single car, will have less than 74.5 tons of coal. In B, we have a sample of 20 cars. So, and you are interested in the mean load X bar. Actually, I have the answers. Well, it's actually in the textbook. So it says for A, the answer should be 13, so it should be 0.2643. In B, because I changed the problem from less than 74.5 to more than 74.5. So I think the answer to B would be 0.9974, I think. Anyway, we're gonna go over this problem. So make sure that the answers are correct. So I will post a new homework on Blackboard this Thursday, and it's gonna be about this chapter 7, of course. Yeah, so we have the whole spring break to solve the homework. So the probabilities of the due date for the next homework would be like after the spring break, okay? Because I know some of you probably are gonna go on vacation or something. So yeah, so the due date for the next homework would be after the spring break.
Professor, are you still
Yes.
accepting late? I have
Say it again. Sorry,
accepting late.
you're breaking up. I don't.
Do you accept late homework?
Oh, say it late homework. And as a policy, I don't really accept. No, I don't really accept the late homeworks. No, because that would be unfair to the other students who submit their homework on time. You know.
No problem.
Mm-hmm.
Would the 20 cars be the N here?
Yes, of course. That's yeah.
Okay.
So we have this sample of 20 cars. Yep. Did you get the 26.43 for A, Janine?
Yes.
That's correct. Okay.
Okay, what is 20 cars? Where's the fucking MU 75 over all standard deviation. Oh,
Right. Does anyone need more time? Did anyone get the second answer, the B? Just check the chat. All right. Let me see the chat. Okay.
I don't know why I'm
Right.
not getting a square root for 20 on the calculator. I press the second button, square root 20, and then I get square root of 5. Like the answer is
Well, that's weird. So we're supposed to
2
is
of square root 5. That's what comes out.
no. So square root
I
of
don't know what
20,
I'm
square root of 20 should be 4.47. So you're supposed to, so we can enter, I guess, 20, and then press on the function square root. Well,
No, usually
do you have like a, is there like something like this, which looks like this? Okay, so if you enter 20 and then you press on this, what do you get?
when I press that, I press 20, enter, I get a error mech.
No. No. I think you, no. I think you need to enter. Oh, you get an error.
Because the way I usually have to enter, I have to put the
Or yeah. Oh yeah.
sign,
Yeah.
put
Okay.
20, I press
Mhm.
enter, and then I get the answer. Now I'm getting 2 square root 5.
Mm, well, square root of 20. If you wanna, I mean, if you wanna simplify square root of 20, that's true. That would be 2 square root of 5. But then, what's
But
the
I
square
need
root
a
of
number.
5? Yeah, because square root of 20 is 4 times 5, right?
Mm-hmm.
And then you can say, well, 4, it's 2 square. So that's 2 square times 5. And then square root of 2 square times 5, you can split this like square root of 2 square times square root of 5. But then square root of 2 square is actually 2.
That's like a whole different exercise, right?
Yeah, that's like a different exercise. But
Hold on. Because I do know that usually the answer for square root is that number times that same number equals the number you're trying to get. So I have a
yeah,
ballpark of
no, but
what
that's like no,
that
but that's yeah, that's true. But that's like for like when you have like whole number, like well,
exactly.
like when we have like a perfect square, like
Mhm,
square root of
mhm.
100, that would be 10
Yeah,
because
we know
10
that it's
times 10, yeah,
Yeah.
that's 100. But of course, 20, you cannot really write 20 like the product of the same number. That's not possible.
I know.
But
I'm having the
yeah,
issue.
yeah. So square root of 20 should be 4 point. That's where that's where I get actually 4.47.
Let me see.
Um,
Root, five, yeah, I don't know what's happening because usually comes
I
out,
mean,
but
if you
I'm
can,
having
if it,
I know the steps,
if
but
you,
not, do it. I cannot confirm the same answer, which that's where I get the practice from. I don't know.
yeah. So if you can, I don't know if you can take a picture for your calculator, like and like put it in the chat. I can try to.
I have the calculator you put on our supplies to get the TI
Okay.
36
Oh, okay.
I
Okay.
have that same exact calculator.
Okay. Okay. So then, so when you press the square root function and then you enter 20, you're saying you get 2 square root of 5.
Yeah, so you cannot really press square root right away because it has the button has 2 functions. So you press
Okay.
second, press the square root where the square root function is. And
Uh-huh.
then the square root comes out on the screen. You enter 20, press
Yes.
enter, and then you get 2 square root 5.
That's weird.
I know. I know.
Like in the screen, does it say something? I don't know. Is there like a?
No, it just gives that the answer would be what I just said, the 2 square root 5.
And if you press enter again.
And then if I press enter again, it comes 2 square root 5 comes out again. I'm trying, and then it just comes out on both sides over and over.
Okay, that's kind of weird.
And then that's
is it just for square root of 20? Like if you try, I don't know, square root of
square root of
just try square root of 5. If you try
See,
square
when
root
I
of
put
5.
square root of 100, the 10 comes out. It comes out.
No,
perfect.
that's because it's a perfect square. But if you just try, for example, square root of 5.
Yeah, I don't know what's going on. It says a square root of 5 again. So
okay, that's.
Do I have to change it? Maybe something else is pressed that I didn't realize I pressed, because before I'm talking about before this morning, it wasn't coming out like this.
You know what you can do is probably can like turn off your turn it off, and then
Let me close it completely.
yeah,
Okay.
think-
yeah.
yeah,
I know that
all right,
messes me up. Like the
Yeah.
steps.
that's weird.
Now I don't remember the steps.
All right, guys. So for A, we're gonna find the probability that the car will have less than just one car, a single car, right? So when it's just one car, then it's about X. This is not X bar. So the probability that a single car will have less than 74.5 tons of gold. So that's the probability that X, just X, is less than 74.5. Okay, this is less than. Okay, and again, it's X, it's not X bar, because here it's about just a single car, just one car. It's not, we don't have a sample here. It's just one car, and X represents actually, that represents the weight of a coal loaded into a hopper car. So that's exactly your X. So we need to find the probability that X is less than 74.5. So so we convert X to Z. But then to convert X to Z, we use X minus mu over sigma, just sigma, okay? When you convert X to Z. Okay, so it's just X minus mu over sigma. So that will be probability that, so instead of X, we're gonna have the variable Z, and then we need to convert this value of X, 74.5, to a value of Z. So that's 74.5, right? That's your X, minus mu. So minus mu. So in this problem, mu is 75, right here. Right here it says mu is 75. So minus 75 over, and then we divide by sigma, the standard deviation, right? So sigma is 0.8. 0.8. So so here we need to divide by 0.8. So this is probability that Z. So we need to compute the fraction. So Z less than 74.5 minus 75. That's a negative 0.5 over 0.8. So this is probability that Z is less than. So negative 0.5 over 0.8, so that'll be equal to 0.60, so negative or minus 0.62, 60.5 actually.
Yes.
And so once you compute, you are done with your fraction, now you can use your chart. So this is less than, so Z is less. So that will be the area to the left, right? So remember, guys, less, that's the area to the left, and that's exactly what we get from the table, the area to the left. That's the area to the left, so I can just use my table, right? Remember, so this is when you have larger, well, actually, we're gonna do larger in the second, in B, anyway. All right, so, yeah, so we can use our chart, and this is negative 0.62, and that's exactly what we, that's exactly the answer, right? So which is equal to 0.2643, which is 62.43%, right? The nearest 10th, that's is negative 0.6. Sorry. Nearest 10th, that's the negative 0.6, and nearest 100th, it's 0.002. So that's exactly what we have here. Okay. All right. So now for B. So in B it says, so we have this random sample of 20 cars. So we have a sample of 20 cars now. So sample of 20 cars. Sample of 20 cars. So the size of the sample n, so n, that's the size of the sample, that's 20. Size of the sample is 20. All right, so now we want to find, the probability that, 20 cars will have a mean load or average load, right, X bar more than 74.5, right? So this is the average, this is the average load or the mean load X bar. So you want the mean load to be more than, right? It says here more than 74.5. So we want to find the probability that X bar, the mean load X bar, is more than 74.5. So more than. This is more than or larger than. Okay, larger than 74.5. So anyway, now we can convert X bar to Z. X bar to Z. Now to convert X bar to Z, we use a different formula, right? So it's X bar minus mu, same as for X, right? For X, it's also minus mu, right? Here, it's minus mu. So the same thing for X bar. However, in the bottom, in the denominator, it's different. In the denominator for X bar, you have sigma over square root of n. Okay, so just keep in mind, difference between X and X bar is in the denominator here. Okay, so I'm gonna convert X bar to Z. So we're gonna make this change of variable. So now it's Z larger than, and we're gonna convert this value of X bar to a value of Z. So that's 74.5 minus the mean, which is the same, 75, we said, right? Yeah, 75 over, and then it's a sigma, which is 0.5, I think. Oops. Sigma is, what is sigma? 0.8, sorry. Sigma is 0.8. So it's 0.8 over square root of n. N is the size of the sample. We said we have a sample, random sample of 20 cars. So that's square root of 20. Right, so that's probability that Z is larger than. So 74.5 minus 75, that's negative 0.5, that's the top. Now, in the denominator, just be careful because of the square root. So it's like 0.8 over, it's like 0.8 over square root of 20. So, this is square root of 20 supposed to be equal to, 4 point, so this is like 0.8 over 4.47. So to get the square root of 20, you need your calculator, okay? Anyway, so then you divide this 0.8 by this 4.47. So then the answer would be, this is actually equal to 0. 0.17. So here in the denominator, that's actually 0.17. Oops. This is 0.17, right? Again, this is how I got this is 0.17. Right, because of this. Okay, 0.8 over square root of 20. Now, so that would be probability that Z is more than or larger than. So 0.5 over negative, actually 0.5 over 0.17. That's actually 2 point, so negative.
It's negative
2.90. Yeah, negative 2.94, I think. All right. So once you're done now with the fraction, now we're supposed to use the chart, but then you need to be careful here because this is more than, right? This is the area to the right. When it's more than, that's the area to the right of this value. Area to the right of negative 2.94. And the area to the right, that's actually 1 minus the area to the left. So this is 1 minus the area to the left. So the area to the left, that's the probability that Z is less than negative 2.94. So this is So this is less and less than. So that's the area to the left of negative 2.94. So 1 minus the area to the left of negative 2.94. So that's 1 minus, and then here we can check your chart. So this is negative nearest 10th, that's negative 2.9. So we need to go to negative 2.9, and nearest hundredth it's 4. So that's 0.0016. So 1 minus 0.0016. So that again, that's nearest 10th, negative 2.9, and nearest hundredth, it's 0.05. So 0.0016. And so the answer is 0.9984, or 99.84%. And I guess that's the same answer as it. Is it 74 or 84? Oh, sorry, this should be 84. All right. Yeah, so it's 99.84 actually. Any question, guys? So just keep in mind, this is very standard. This is like a standard problem in the test or the final. First, you will have to compute the probability that x is less or more than something, or x between two things or two numbers. And then in B, the B would be about the x bar, right? And just keep in mind, you need, in both cases, you need to convert your x or x bar to z. But the thing is, for x bar, when you divide by a sigma over square root of n, the size of the sample. All right. Any question, guys? Otherwise, probably we can move to the next
Professor, I'm sorry. Do you know what
section? Yes.
was D, E, G
Yes.
on the calculator?
D, E, and G?
Yes. I'm assuming that's like
E,
a
yeah. I think because E is the exponential, I guess. That's like a exponential function. D,
yeah, my kids, I'm gonna.
I'm not sure about the D. The D and G, I don't know. I need to take a look, but the E, that's exponential.
Where does it have to? Does it have to be on NORA or SEI as I guess a scientific calculator, or maybe that's why I'm getting.
You're still getting you're still getting the square root of 5 equal to square root of 5.
Yes.
Okay, you know what? We can probably meet later. I mean,
yeah.
After the lecture, like
Okay.
I can, if you show me your calculator, I
Okay.
can probably, yeah. Mhm.
All right.
All right. Okay, guys. So I guess we can move. I mean, we are done with this section 7.5. I think we did plenty of examples. So yeah, I think we are ready to move to the next and the last section in chapter 7. So this is section 7.6. So yeah, so this is 7.6. It's about a normal approximation to binomial distribution. Normal approximation to, I'm not sure if we're gonna finish this section today, but probably gonna finish it tomorrow. It's a very short section. We're gonna do probably a couple of exercises. And then, as I said, so this week, we're gonna probably finish with the chapter 7. So after the spring break, we can start chapter 8 and chapters 8 and finish chapters 8 and 9. Yeah, so this is normal approximation to binomial distribution. Binomial distribution. So binomial distributions, remind you guys, that was a chapter, you know, sections 6.2 and 6.3, right? That's actually our homework number 5, right? So just to remind you here, binomial. So we discussed binomial distribution or binomial experiment in sections distribution in sections 6.2 and 6.3, right? And that's actually your homework. So your homework homework 5 was about this these two sections plus section 6.1. Anyway, I'm gonna just remind you very quickly, you know, how to what's this binomial distribution, etc. Very quickly, because I know, I mean, if you spend time solving the homework, then you probably know what I'm talking about here. But anyway, so in a binomial, just to remind you, so in a binomial, we have this binomial experiment. You know, we have our two outcomes. There's a success, either success or failure, and then there's P, which is the probability of success, probability of capital S, or success, capital S, and capital F stands for failure, right? And so Q, that's probability of failure, and that's always 1 minus P. Okay. And there is N, right? The number of trials. And there is R. That's our variable, actually. This is R, the number of successes. Number of successes. That's our, so R here. R is the variable of this binomial distribution. R, this is the variable of binomial distribution. Right? Because again, guys, just to remind you, what do we mean by, you know, probability distribution? Probability distribution is just to assign, you know, for each value of your variable, some probability, right? You assign a probability for each value of your variable. For example, here, number of successes are, you can find, or you can compute, for example, probability that R is 0, probability that R is 1, probability that R is 2, etc. Right? So you assign for each value of R, you assign a probability, right? And that's what we mean by a probability distribution. Anyway, so R, that's your variable of that's the variable of the binomial distribution. Right? And of course, the goal here is to compute this probability that the number of probability that the number of successes is equal to R. So we need to find this, right? Probability of R. All right. So we said, you know, to find the probability of probability of R, our successes, we can use this table number 2, right? This is table number 2. But the problem with this table number 2 is that, you know, the number of trials N, N is actually the largest value of N is 20, right? Number of trials N, the largest value of N in the table, number 2 is 20, right? So mark. So here, I'm just saying that the largest value of N in the table 2 in this chart is actually 20. That's the largest value. And actually, I think there are some missing values between, let's say, I think 15 and 20, or, you know, there's some missing values, right? Between, I don't know, 15 and 20 or something. Anyway, so the question is, so how do we compute this probability of our successes for, you know, large N? Right? So when N is large, when N is more than 20, right? So question, so when N is more than 20, so when N is more than 20, okay. So of course we cannot use our chart because the largest value of N is 20. Well, we can use the formula with, you know, we have this formula with the factorial. We can use the formula with the factorial. So let me just remind you the formula. But anyway, we won't use the formula. So it's just I'm just saying here that, you know, if you cannot use the table, then in theory, we can use our the formula with the factorial. So that which is the following. So probably that the probability of our successes is equal to, supposed to be equal to n factorial over r factorial times n minus r factorial times p to the r, probability of success to the power r, times the probability of failure q to the power n minus r. Right? So again here, the factorial exclamation point, that's factorial, it's called factorial, right? Where n exclamation point, that's n factorial. And what do we mean again by this n factorial? So for example, if you say 5 factorial, that's like 1 times 2 times 3, you multiply until 5, right? So last number would be 5 because that's a 5 factorial. So anyway, so like here in this case, that would be 120, right? Etc. So in theory, if you have n number of trials more than 20, we can always try to use this formula. But you know, if n is very large, I don't know, let's say n is 100, for example, and I say n is 100, you have 100 trials, right? Then this n factorial is gonna be a huge, right? It's gonna be a very big number. This is a huge, this is a very big number, very big number, right? This is like, you know, 100 factorial is like, you know, it's like 1 times 2 times 3 times 4 times etc. And the last number would be 100, right? So that will be a very, very large number, right? This is going to be a large number. So then the calculators require large computing power. Okay, so you're gonna need very powerful calculator. Okay, so then we're gonna need a very powerful, I guess, calculator. Okay, so let's say we have very basic calculator, right? So I cannot really compute this 100 factorial, etc. Okay, so then, well, then there is another way actually to compute this probability of our successes when n, for example, this number of trials is 100. So instead of using this formula, which require a very powerful calculator, what we can do is we can use the following theorem. So it turns out that we can approximate a binomial distribution using a normal distribution. So the idea here, so instead of using powerful calculators, we can use the following theorem. We can use the following theorem, and so this theorem actually, as I said, it's just it says that we can approximate following theorem. So which says, so it says that we can approximate a binomial distribution using normal distribution. We can approximate a binomial. So this is why normal distribution are very powerful. So even a binomial, you can approximate a binomial distribution by a normal distribution. Binomial distribution by a normal distribution. All right, so the theorem says the following: normal distribution. Right, so if you have this like very large number of trials, like as I said, like here 100, right? So then you can use the following theorem. So the theorem is the following. It says the following. So theorem. So let's say consider a binomial distribution. We have a binomial distribution. Now, in a binomial distribution, you have a N, you have P, you have Q, you have R, with N number of trials, P, that's probability of success, Q, probability of failure, and R, number of successes. Then, well, there is actually a condition here. So if is a hypothesis, so you need to approximate this binomial distribution or normal distribution, you need N times P. So if N times P is more than 5, so this is more than. So if N times P is more than 5, and N times Q is also more than 5, and N times Q is more than 5, okay, so then the variable R, the number of successes, has a then R. So the conclusion is that, so then R, the number of successes, has, so the R can be, so number of successes can be approximated by, a normal distribution, So again, keep in mind, guys, so what does it mean for us that the variable is approximated by a normal distribution? Well, if you have a variable that can be approximated by a normal distribution, then you can convert the variable to Z, right? And then once you convert to Z, then you can use the chart and then you get your answer, right? So that's why it's important that your variable can be approximated by a normal distribution, because then you can just use convert X to Z, your variable to Z, and then use the chart, and then you're done, right? So yeah, so be approximated by a normal distribution. So in other words, here you can convert R to Z, right? With population mean. So here's your mean. So population mean mu. So we know what will be the mu. It's going to be N times P and standard deviation sigma. And remember, we said the mean of a binomial distribution is N times P, and the standard deviation of the binomial distribution is the square root of N times P times Q, right? This is the same as in section 6.3, right? This is a standard deviation sigma, which is square root of N times P times Q. So this is exactly what we had in section 6.3. So this is the same as section 6.3, right? Remember section 6.3? And actually, I think we have a couple of questions about this in the homework. So if you have a binomial distribution, then the mean would be N times P, and the standard deviation is square root of N times P times Q, right? And the thing is, so here, so what we are saying is, in some sense, so if N is large, if the size of the sample is large, so if N number of trials is large, if this is large, then we can convert R to Z. We can convert R, number of successes, to Z. Okay, and the formula would be Z equal to, so R minus mu minus the mean, right? But the mean is What's the mean? Mean is n times p. So r minus np, okay, over sigma, the standard deviation, right? Which is square root of n times p times q. Okay, so again, the np, that's mu. This is mu. And the denominator, that's your sigma. That's your standard deviation. Right? So this is like, convert x to z, right? X minus mu over sigma. So we can do the same thing for r, for the number of successes, when the number of successes is very large. Okay, so if you have like number of trials very large, and so you cannot use the chart, the table 2, right? And n is very large, so then you're gonna need a very powerful calculator, right? So instead of that, we can just use normal distribution. I can convert your r to z, etc. Okay. So let's have a couple of examples. What time is? Do we have time for an example? Oh no. Okay. All right, guys. You know what? We can stop here. Tomorrow I'll give you a couple of examples, and then we're gonna be done with this section. And yeah, probably I will start a new chapter after the spring break. So tomorrow we're gonna just do some exercises and practice a little bit. All right. Thank you for listening, everyone, and hopefully I'm gonna see you tomorrow. You can say, I mean, if you wanna check, your calculator, see if.
Yes.
So let me just stop recording and stop recording and stop sharing.